Uh, Good afternoon. Welcome to the colloquium. It's a great pleasure to have the first sort of in-person talk for a long time. And we have Arvind Ayyer from the Indian Institute of Science, and he's going to talk about a multi-species, totally asymmetric zero-range process and Macdonald polynomials.
Okay, can you hear me? Is it okay? Okay, thanks a lot to Amri for organizing this and for inviting me. I confess I'm not quite sure what to do now that I have to give a talk in front of a stage, back to stage fright and all that. So I want to, yeah, so it's great to be back in sweaty, humid Chennai, brings back fond memories. Okay, so I want to tell you about some work that I've been doing jointly with Olya Mandelshtam, who's at Waterloo, and James Martin, who's at Oxford, on some connections between Macdonald polynomials, which are perhaps one of the most important families of symmetric polynomials have emerged in the last century, and a particle process, which is also quite important for the physicists, mention why. And we found this very interesting connection between the two, and I'd like to mention it. So I apologize to those who were there in Venkatesh's conference. Some parts of these are overlaps, but the latter half is new. Okay, so let me use this. Okay, so let me just go through basics of symmetric functions. I'll go pretty fast because I assume most of you are familiar with this. But of course, if there are any questions at any time, please feel free to interrupt me. So suppose we have a family of commuting indeterminates, x1, x2, etc. Then you consider the algebra of symmetric functions with, let's say, rational coefficients. Then there are several. Then this is a vector space, and it's graded by degree, for example. And there are several natural bases of these vector spaces, and these are the classical ones: the monomial symmetric functions, the elementary symmetric functions, the complete or the homogeneous symmetric functions, and the power sum symmetric functions. So these are older, maybe 19th century or so. But the sure functions is like the one ring to unite them all, and so it's sort of, in some sense, the most natural and basis, and it has several connections to other areas of mathematics. Now, if we generalize to allow coefficients to be rational functions of q and t, where q and t are two extra parameters, then Ian Macdonald came up with this amazing two-parameter family of symmetric polynomials, and these are now called the Macdonald polynomials. And these are simultaneous generalizations of several classes of symmetric polynomials, which include the sure polynomials, which I mentioned below, but other polynomials as well. It's known such as the Hall-Littlewood polynomials and the Jack polynomials. If you don't know about these, you can forget about it. It's just to give you some context. And to define the Macdonald polynomials, I have to give you, there are two ingredients, and to do that, to define them, I need this symmetric product, this inner product. So this is defined in terms of the power sum symmetric function. So if you have, so the bases for lambda are the partitions, the integer partitions, and so if lambda and mu are two partitions, the inner product of p lambda and p mu. So the inner product is defined by stating that these two are orthogonal. The p lambdas are orthogonal, and their norm is sort of this quantity, where z lambda is a standard expression in terms of lambda. I'm not going to define it because I don't really need it. But let me just say that they are uniquely determined by these two properties, which says, first of which says that p lambda has a monomial expansion in terms of the monomial symmetric functions, where the sum only involves partitions which are smaller than or equal to lambda in dominance order, and the diagonal term is 1. And they are orthogonal with respect to the inner product that I defined. So it's highly non-trivial that these two properties are sufficient to determine the Macdonald polynomials completely, and these are called the triangularity and normalization. Okay, so there's another family of polynomials which are related to Macdonald polynomials and in some sense equivalent, and these are called the modified Macdonald polynomials. They were defined by Garcia and Heyman in '93, and they are usually denoted as H tilde of lambda, and they're you can obtain them using plethysm, but and not on p lambda, but something related to it. Okay, but let's not go into that. There's again an axiomatic definition, and I don't want to get into it, but these three axioms sort of again uniquely define the modified Macdonald polynomials.
So that inner product is the
Sorry.
same one?
Sorry?
The last step, the inner product.
Yeah.
Which inner product?
Yeah, it's the same one. But these relations are a bit more complicated, and this bracket means plethysm, and so I don't want to get into it. It's a bit of a pain.
But so to speak, they live in the same space that the
Yes. They say, and in some sense they are simpler. So if you expand the p lambdas in terms of monomial symmetric functions, coefficients are rational functions in Q and T. But the modified Macdonald polynomials are, when you expand them, you really get polynomials, and the expressions are also more compact. So in some sense, they are more simpler. Okay, so let me tell you just some history. So about combinatorial formulas for the modified Macdonald polynomials. So Hagelin, Heyman, and Loehr in this paper in JAMS gave the first sort of genuinely non-trivial formula for the modified Macdonald polynomials. And this formula is a sum over tableaux, certain tableau, and there are two statistics, the MAJ, the major index, and the inversion number. I'll describe this in more detail. This is relevant to what we are going to do. Corteel, Mandelshtam, and Williams, they gave a formula for the usual Macdonald polynomials using some things called multiline queues, and these have connections to another particle process called the multispecies asymmetric simple exclusion process. I'm not going to define it, just to say that there is a connection with statistical mechanics. And building on this work, the first three authors, and Sarah Mason and Lauren Will and Jim Hagelin, they gave a formula for the H tildes, again as a sum over tableau. So they build on this work, but and use the same statistics, but with many fewer terms. And in a completely unrelated direction, Garbali and Wheeler, they used the theory of integrability to give a combinatorial formula for H tilde lambda. This is another kind of statistical mechanics model, colored paths. Okay, so the motivations for our work are two. So in the article that I mentioned before, these people's, so I'll just call them CHMMW. So they gave a conjectured formula in terms of using MAJ, the statistic that I mentioned before, and a new statistic that we'll call QUINV. And our in the first paper, we settled this conjecture in the affirmative. Our second motivation was the connection with the multi-species ASEP that I mentioned. And this was used to compute p lambda. And the question was, is there a particle system which can be used to compute H tilde? So that's the other motivation. I want to spend more time on the second today. And we show that this works when q equal to 1. So we have not yet solved this in full generality. Okay, so let me start with some notation. So let lambda be a partition, and as usual, these will be in weakly decreasing order. So unfortunately, historically people have used yet another pictorial notation for partitions, and I'm sorry, but we are kind of forced to use that. So the diagram of type lambda, it consists of k bottom justified columns, where the ith column has lambda hypothesis. So if you rotate the whole thing clockwise by 90 degrees, you get the usual Young diagram in English notation. So this is the diagram of 3, 3, 2, 2, 2, 1, 1. Unfortunately, okay, there are already too many things, but okay, this is one. So we will consider filling. So a tableau is just a filling of these with positive integers. And unlike semi-standard or standard tableau, we have no restriction. You can fill anything with anything, and there's no decreasing or increasing in any direction. And tab lambda n is the set of all tableaux of type lambda with entries in 1 through n. Okay? And so there's a typo here. I mean, here there should not be an n. So in general, a filling, you allow any positive integer. And the monomial weight of a tableau is denoted x to the sigma. It's just x1 to the number of 1s, x2 to the number of 2s, and so on. So in this example, it's x1 to the 5, x2 to the 3, x3 to the 6. Okay. So let me describe the two statistics. So the major index is going to be important. So a descent in a tableau is a pair of entries in cells u and v, where u is directly above v, such that the value at u is strictly greater than the value at v. Okay? And then we say u, the cell, belongs to the set of descents. Okay, now the leg of a cell, unfortunately, counterintuitively, is the thing above it. So the leg is the number of cells above u in the same column.
It's the 90-degree rotation, right?
Yeah. So
The leg is
yeah, so the leg, it should have been the arm, whatever. Okay. So again, this is not my notation. I apologize. So this Hagelin-Heyman Lur in their JAMS paper, so sort of set the notation. They came up with their own notation for many things, and now it's kind of.
You just didn't want anybody else to work on it.
Maybe, but we did work. So that also failed. Okay, so I'll do an example in a second. But the leg is basically the number of cells above you. So it's not a leg, maybe it's a raised hand or something. I don't know. And the major index, this is again notation borrowed from the theory of permutations. The major index is the sum over the 1 plus the leg length. So you include the cell, then you get 1 plus leg of u, and you sum over all u in descent. So for this example, you look at all cells which are strictly, where the entry in the cell is strictly larger than the cell below it. And then you count how many cells are there above them, including themselves. So this has 1 plus leg, this has leg length 0, so this contributes 1, this contributes 2, 1, 1, so you get total.
How come you have a 1, 3, 2? I mean, what's happening?
Where?
In the second column?
2, 3, 1? 3 is larger than 1, no?
No, they don't have to be increasing.
No condition whatsoever. So, I mean, as I said, there's no restriction on anything. Okay. Yeah? Okay, so you get 5 from here. I hope this computation is clear. Okay, so now the other statistic, the inv statistic, is a little more complicated, and this requires 3 cells. In this case, u and v, again, as before, u is directly above v in the same column. And w now has to be in the same row as u. Okay, so they form like a gamma shape. So that's why I call them gamma. Okay, so forget about degenerate triples. I mean, so the basic idea is these form an inversion if, assume that these 3 cells are distinct, then either when you read clockwise or counterclockwise, you will find them in increasing order. Only one of them is possible, right? So they form an inversion if the entries increase as we go counterclockwise. And forget about degenerate cases, but basically this forms an inversion because 1, 2, 3. You go counterclockwise, you find there is a place at which you can start, and you have the 3 in increasing order. It's not possible. So if I go clockwise, at no point will the entries be all increasing. So these are increasing. There are some cases equality is broken in some complicated way. I can describe that later. So this is not an inversion because the entries increase as you go clockwise. Okay? And in this same running example, whenever you have, okay, so this pair U and V contributes 3 inversions, because whenever these two are equal and this is not equal to these two, then you get an inversion. This does not contribute an inversion. So you get an inversion from these 3 threes.
The third one will be in the right or?
Has to be in the right. Yeah, so W has to be to the right. Yeah, that's why it looks like a gamma. Otherwise, it will not look like a gamma. Yeah. Okay. Right. So that's the idea. So it's quite complicated. Everybody agrees. So the theorem, this remarkable theorem of Hagelin-Heyman-Lahr, is that the modified Macdonald polynomial can be written as a sum over all tableaux, q to the maj, t to the inv, x to the sigma. So I forgot to mention one thing, that there's another nice thing about the modified Macdonald polynomials. Where is the chalk? Is that h tilde lambda x qt is equal to h tilde of lambda prime x tq. So, and this again, so it's a non-trivial fact that if you conjugate the partition, it's like flipping q and t. But that is again not visible from this, because one is one has to do with descents and one has to do with these complicated triples. I mean, so there's a lot of nice magic going on here.
I have a couple of questions. I'm not sure. So a Macdonald polynomial, we don't have anything like this.
Right.
So the whole point is that okay, we can't do it for Macdonald, but
this is nicer.
Related and it's much nicer.
Yeah, you can see this is a polynomial expansion.
Is that the reason this is so important, or is there something else? I think that I don't know.
Well, I think there are other connections to geometry. At least Mark Heyman is motivated by those things. So, but I'm not familiar with that side of the thing. Yeah. Not, yes, I now forget. Yeah, so in certain special cases, I think they will come up with that. But
can I have the mic, please?
Excuse me.
Mic. Yeah, no. So I was just wondering, if you calculate these, can you calculate Macdonald
Yes,
easily?
yes,
Okay,
you
so
can go
it's
back
easy to go between this and that.
Yes, yes.
Okay.
Yeah, and but to arrive at the definition is harder, but somehow they're easier to calculate. Okay, anything else? So yeah, here inv sigma is of course the number of inversions, which are number of these gamma triples where they go counterclockwise in increasing order. Okay, so our new statistic is so closely related to the gamma triples, it's a bit ridiculous. So these are, so now you look at 3 cells in, again 3 cells, but we say that they form an L triple if again U and V are in one below the other, one above the other, and W now is in the same column as V, same row as V. And again, you forget about degenerate cases. And now we say that they form a Q inversion if, as you go counterclockwise, they are increasing. Okay, so the only difference is that we moved the W from top to bottom somehow. Okay, and again, forget about ties for a moment. So again, these are the Q inversions.
What is so Q about it?
I'm going to say that. Yeah. Just hold on for this slide. You anticipated my question. So again, this is a non-example of a Q inversion. And okay, forget about degenerate cases. So again, in this case now, if you have 2 entries which are equal one above the other, then the third entry should not be equal to that. So we have 4 contributions to this UV pair from W, which is this, 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 and this. So that's the 4. And quinv be the number of Q inversions, and why quinv, which is Amri's question. So this has to do, so if you remember, I told you about the ASEP and this multi-line Qs. So that Q, so there's a connection between those Qs, as in Q, U, E, U, E, S, and so we call them quin. I mean, it's not, yeah, Olya had the idea of calling
It's not the other Q.
It's not the other Q, no. And it's a bit counterintuitive because the Q power is the match and T power is the quin.
Otherwise, it would be a Q dash in, right? If it
Ah.
was a Q analog, like Q
Yeah,
star.
yeah. So this is our theorem that the modified Macdonald polynomial can also be written as Q to the match T to the quin. Okay, and you would think, oh, I mean, come on, this has to be bijective. I mean, one is just these gamma triples, and one are these L triples, and you should be able to fudge it around and come from one to the other. But we've tried quite hard, and it's certainly non-trivial. It's not easy.
Does it take you closer to the symmetry of T and Q?
No. Doesn't help with anything. It helps for our particle system. So somehow, because of this queuing connection and the particle system connection, we think these L triples are more natural than the gamma triples, and but
So what you're saying is that if you look at tableau with fixed match, then you would think that there is a bijective, but then you go, wow.
Yeah. So let me repeat Mohan's comment. Is that so? If you fix, both have Q to the match, right? So I can fix all the content for every fixed content and every fixed number of descents. I mean, a fixed major index. The contribution of T to the quin is the same. So, but and there doesn't seem to be any obvious way of going from one to the. I'm getting a bijection which flips the gamma triples to. I mean, we have even more refined conjectures than that, but it's crazy. Yeah, it's just we don't see any simple bijective proof, and we tried quite a bit. So here is one example. So I look at lambda equals 2, 1, 1. So remember, in this funny notation, 2, 1, 1 looks like that. And I just look at two variables. So I have x1, x2. So I'm only allowing fillings with 1 and 2. So in black, I have put the contribution. I mean, I've put the R contribution, and in red, the Hagelin-Heyman-Miller contribution. And of course, when all are the same, their contribution is the same. But when you have terms like x1 cube, which have content x1 cube, x2, then there are more, and then they don't match, you see. So I get q naught t squared here, but I get q naught t squared here for HHL, like that. So they don't really match at all. And in such simple cases, maybe you can come up with a bijection. But in general, it seems very, very difficult. And the total formula looks like this. Okay, so it's quite tantalizing. Okay, so sorry. So yeah, so this was kind of the first part of the talk. So now I want to describe the connection with the particle process. Okay, so let me just say something about zero-range processes. So they were first defined by Frank Spitzer in this remarkable paper in 1970. In this single paper in Advances of Math, he defined like a bunch of stochastic processes, which like the contact process, the exclusion process, the long-range exclusion process, so the zero-range process. All of them are defined in this paper, and they have led to like a remarkable amount of work. Many of these are on infinite graphs, and they come with their own complications because in continuous time, infinite continuous time, processes are non-trivial to define.
So these are supposed to model some sort of flow? Or?
Yeah, I mean, so contact process models epidemics, for example. There's a voter model which models how voting patterns are supposed to evolve over time, things like that. Yeah, so the exclusion process models like hopping of.
That's like some fluid, right? Glass.
Yeah, right. Or not necessarily, or heat flow or something. Yeah, so yeah. So at that time, I think he just wanted to do it systematically, and but then they sort of took on a life of their own and so on. And these are continuous time processes, and in principle we can define them in any graphs, and you need some extra data about sources and sinks or something sometimes. We will consider this on the ring. So the ring is the graph is the cycle. So n vertices arranged in the form of a cycle. And in its simplest formulation, they will have k indistinguishable particles. So we will just think of them as each particle will be a 1. So a configuration will just be any allocation of particles to the sides. So each particle will contribute a 1. So for example, if n equals 4 and k equals 3, you can have configurations like this, 1, 0, 1, 0, like that, which means there's a particle at site 1, 1, 0, 1, 1. There's a particle at one particle each at sites 1, 3, and 4, or you can have something like 1, 2, 0, 0, which means there's one particle at site 1, 2 particles at site 2, like that. So that's how we will think of.
It's just a line graph.
Yeah, yeah. This is just a configuration tau. It's just I'm just labeling the number of particles in the n sites. They're indistinguishable, so it doesn't. And we will think of particles. So for us, particles will move counterclockwise. We are looking at a totally asymmetric version where particles only move in one direction. There are, of course, any number of generalizations. And each particle will only move one side to the left. I mean, you could have longer range motions. So here, why is there interest in this? And that's what I want to explain. So suppose f is any function from the non-negative integers to the reals such that f of 0 is 0. And then the transition is that any particle can jump from side j to j minus 1, of course mod n, with rate f of the number of particles at side j. So in this case, this will go to, 2, 1, 0, 0 with rate f of 2. And I also go to 0, 2, 0, 1 with rate f of 1, like that, because there's only one particle at the site, and it's moving counterclockwise.
So the rate you mean that's the exponential distribution by the way?
Yeah, exactly. Yeah. So these are continuous time processes. So we have this rate, and all you need for the rate is that this should be a positive function, which it is. And why is this called zero range? Because the rate at which particles move out depend only on the content at that site. It doesn't depend on anything further away. So it's zero range. It doesn't have any range. It only depends on that information at the origin site. And the main interest in this comes from the fact that no matter what f you choose, the stationary distribution is always a product measure. And stationary distribution is the long-term distribution. So if you wait long enough and look at the probability distribution, it will always be a product measure. Which means that there exists a function g such that the stationary probability of the tau that I defined earlier, tau 1 to tau n, is the product of g of tau j's. Okay? There are no correlations.
Is this a difficult, is this a non-trivial thing to prove?
No, once you know it, it's easy to prove. But yeah, it's it's just.
So it just comes from the zero range?
Yeah, that's all. And this g is like the antiderivative in some sense of f. And this z is just the normalization to make it a probability distribution. Okay, so what I mentioned so far is a single species process. There's only one kind of particle, but you can have multi-species variants where there are different kinds of particles. So multi-species means you have like a first class particle, a second class particle. So different classes of particles with different speeds in a sense or something. And these Japanese groups have studied several variants. They come from the theory of integrability, and they add more and more complexity. The rates are different. Many particles move at the same time. They have all kinds of complicated things, but they're all integrable. So they are able to use Yang-Baxter equation and all this machinery, and they're able to do some computations. But we have kind of the simplest version of this, which was studied by Takeyama. As far as we know, it's not published. He's put it on the archive and kind of forgotten about it. Didn't try to publish it. Anyway, so let me describe the configurations now of this multi-species process. So again, fix a partition. So this will be the content. Okay, so I'll give an example. So there'll be k particles. So lambda 1 is the first particle, lambda 2 is the second. There can be equalities. So you can have several particles which are the same and so on. So if we write lambda in frequency notation, which is 1 to the m, which means the m1 ones in lambda, m2 twos, and so on, then the sum of these mi's, multiplicities, is k. So as I said, there are m1 particles of species 1 and so on. And we have again n sites as before. Now any configuration is what we call a multi-set composition of type lambda with n parts. So what it is maybe easy to say with an example. So suppose lambda is 2, 1, 1 and n is 2. So you have 2 sites. Each site will have some of these particles, and it will be a multi-set because you're allowed repetition. So everything. So this means there's 1 particle of type 2 and 2 particles of type 1, like that. So everything can be in the first site, for example, or there can be 2 ones on the first site and 1 2 on the second, etc. So these are the 6 configurations. Okay. So now let me describe the transition. So this involves another parameter. So you again have a single particle jumping from site j to j minus 1, just like in the single species zero range process. And we'll think of the particle, the 1 being the strongest particle and then 2 being weaker and so on. And their rates are governed by another global parameter t and these site-dependent parameters x1 to xn. Okay, and what it is as follows. So for each site j and every integer a, you have an exponential clock of index a which rings at rate 1 by xj times t to the a minus 1. So you'll have at the jth site you'll have a clock with rings at rate 1 by xj, then t by xj, t squared by xj, and so on. When the jth when this clock rings, if j has less than a particles, nothing happens. Otherwise, the ath highest particles jumps to site j minus 1. Okay, highest meaning in natural order, integer order. So let's look at the following example. I think instead of giving the formal definition, because there's a slight issue with equality of particles. So I think this example should illustrate this. So look at this configuration. So lambda is 2, 1, 1, n is 3 now, just to break some ambiguity with the cyclic order. So all of the particles are on site 3. So with rate 1 by x3, the 2 jumps. With rate t by x3, the first one jumps, and with t squared by x3, the second one jumps. But those 2 ones are of course indistinguishable. I don't know which jumped, so they add. So with t plus t squared by x3, one of the ones jumps to the left. Okay, and this you can see how to generalize. And just to give another example, from this configuration 2, 1, empty 1, the 1 moves left with rate 1 by x3. This 2 moves left, which means comes to the third site with rate 1 by x1, and this 1 moves left and comes to the third site with rate t by x. Okay, so that's how it goes. Okay, any?
Why don't you move to the center?
Yeah, it did. This the first case.
Oh, there are only 2 sides. Okay.
No, there are 3 sites, but it's moving counterclockwise. So it's.
Oh, okay.
So from here it moves to this guy moves here.
Why is the last one? Why is it t factor?
Yeah, because for the same reason there's a t factor here. So there's a 2 and a 1 here, right? So in this case, the 2 jumps, when the highest particle jumps, there's no factor of t. Next highest will get a t to the 1, then t to the 2, and so on. And whenever there are equalities, you will just add all of them. So it will always be a contiguous power.
So the height is always like among all particles, not just the particle of that type.
Right, total number of particles. Yeah. So that's why it's a t plus t squared here, because this has 3 particles. And you can see the connection to the t numbers, right? 1 plus t squared. So the stationary distribution has this complicated, well, not terribly complicated expression. So remember, this is for this example that I mentioned before, partition 2, 1, 1, n equals 2. These are the formulas. And if you sum all of them, you will get exactly the modified Macdonald polynomial with 2, 1, 1 in x1 and x2, because there are only 2 sides, q equal to 1, and t being this extra parameter. And that is the content of the theorem. So the partition function in general is given by the sum of these weights. And for the multi-species TAZRP on n sides with particle content given by lambda, it's exactly h tilde of lambda in x1 to xn, with q equal to 1 and t being what I said.
Quick question. If you also want to include a q, do you also want to permit maybe 2 sides?
So do you anticipate that if you somehow want to extend, put the q parameter in, there'll be a 2-side, it jumps to a new position? Oh.
No. So yeah, that's a good question. So I had mentioned this work of Corteel, Mandelshtam and Williams. So the intuition from their work is that the q will enter into the transitions that take you from the first side to the nth side somehow. So right now we have kind of translation in, not exactly invariance, because x1, x2, xn are arbitrary, but you have a kind of covariance. If you rotate, then you shift the xi's, right? But once the belief is that once you put the q, then all of that niceness will break down. There are further nice things that are going to happen, and I'll say something. So if you would have noticed, this factored nicely. There's some factorization going on. That is something special to q equal to 1, and I'll mention that. I should mention this. So remember we are on the ring. So there are n sides. So what we should expect from basic symmetry considerations is we should expect circular symmetry. I mean, if you shift xi by xi plus 1 mod n, this partition function should be invariant. But this is a full symmetric function involving all symmetries. So there is something nice going on, which is more than you can expect from Noether's theorem or something. Okay, so let me just recall the q notation. So the q numbers, typically one uses the parameter q of are 1 minus q to the n by 1 minus q, which is just this. And the q factorial is the product of these. The q binomial coefficient and the multinomial coefficient are defined appropriately. So these are polynomials in q. Well, all of these are polynomials in q. So let me tell you, as I mentioned earlier, let me tell you about the properties of h tilde lambda. So if lambda is lambda 1 through lambda k, h tilde lambda factors already into components which depend on the conjugate partition. So let me go through this example first. So if I look at 2, 1, 1, my running example, so you write, so the conjugate partition of 2, 1, 1 prime is 3, 1. And so you will get h tilde with 1 raised to power 3, which is this 3, and h tilde with 1 raised to 1. Okay, that's the general way this factorization goes. So all you need to know is h tilde with any number of 1s. Then you can write down the h tilde for anything. And moreover, so h tilde of 1 to the, if you raise it to, if you have m 1s, then it can be written as a sum over all partitions of m of m mu times this multinomial coefficient, that t multinomial coefficient now. Okay. Okay, just let's do a sanity check. So from the point of view of the m TAZRP, having particles labeled 1, 2, 3 is pretty much the same as having any 3 distinct labels, right, in something like 217 and 23. Okay? But these partitions are very different, right? I mean, this h tilde lambda for this lambda is going to be massive. You'll have a factor with 23 ones and 17 ones. And therefore, for the above result to be true, we need this modified Macdonald polynomial indexed by this to divide this. Otherwise this thing won't make sense. And because of this factorization, this turns out to be true. Okay, so this sanity check works out. And so let me. So the idea of the proof. How much time do I have actually? So depending on that, I'll go through. But the idea is to construct a process on tableau which will project to the TAZRP. And that's what I want to describe now.
About 20 minutes. I mean, we started a bit late, right?
Okay. So so I really want to describe that process. So we have a Markov chain on these tableaux that I mentioned when I was talking about the combinatorial formulas. And it's complicated, the process is complicated in general, but when the partitions have distinct parts, it's relatively easy to describe. So that's what I want to go through. Okay, so suppose lambda is a strict partition, which means it has distinct parts. And U is a cell in the diagram. So remember our diagram had this funny convention. So 2, 1, 1 was like that. So suppose U is a cell, then south of U is the cell directly below it if it exists. It's a natural notation. Unlike many of the other things, this notation is natural, maybe because it's our notation. Okay. So I'm going to define a map from tableau, from the set of these tableaux onto itself as follows. If the cell in the south of U is the same as in the cell below U contains the same element as the cell U itself, then RU of sigma is sigma. Okay? So it doesn't change. If not, you look at the cell U in sigma and keep going up and see how far you can go when the entries, as the entries keep increasing contiguously one after another, mod n. Okay? And you construct the maximum such sequence of cells. Okay? And what you do is you just increment all of them by 1, mod n again. Okay? So increment the content of each cell in this chain and leave everything unchanged, and you call this resulting tableau RU of sigma. So let me give an example. So let's consider this tableau for the shape 3, 2, 1. So if I look at the cell 2, 2, that's this one, its content is the same as the content to the south of it. So when you apply RU, it does not change. R of that U equals 2, 2, it does not change. Same for 3, 1. So I should say 3, so the row index is read first. So it's 3, 1. That is this cell. Okay? So these two do not change. Let's look at the others. So let's look at 1, 1, which is probably the most non-trivial case. So so there's nothing south of it, so we can move on. So look above it. We are looking at n equals 3, so 3 plus 1 is 1. So that is part of this chain. Then 1 plus 1 is 2. This is not 2. So the maximum maximal block is this 3, 1. And what R will do will increment 3 by 1 and 1 to 2. So you'll get this. Everything else will remain unchanged. For 1, 2, this entry is not 3, so it's just the singleton cell, so the 2 will become 3. For this, there's nothing above to do, so the 3 will become 1. And for this 1, this entry is not 2, so this is just again singleton. Okay, so that's the idea. Okay. So to define the transition, I need the notation of a lower arm. So for a cell, the lower arm is drawn in red. It's the set of all cells to its left in the same row and to its right in the row below, strict right. And there's a notion of upper arm which is very similar. I don't need it, but it's important in the proofs. Okay, so now I can describe the process on tableau. So I'm going to define, so remember my tableau, I have this partition lambda like that. I'm allowing all possible fillings, and I'm going to pick a u. I start with any filling, I pick a u and I apply this. I apply this RU transformation with a rate. So I want to describe that. So suppose sigma is a tableau and u is a cell such that sigma of south of u is not equal to sigma. Then down of sigma u is the set of all cells in the lower arm of u which are equal, which have the same content as u. Then we attach an exponential clock with rate t to the down of sigma u divided by x of sigma u. Okay, and when this clock rings, we make a transition to RU. So from every tableau sigma, we make multiple transitions, each depending on u, a cell, which is such that it does not have the same content as the cell below it immediately. So our main proof strategy is that this process will lump or will project to the multi-species TAZRP.
Meaning in terms of the contents of the...
No, I'll describe the projections. It depends on the bottom row. I'll describe that in a second. But this process does not lump to the or project to the multi-species TAZRP when you have repeated parts. Then one needs to do something much more complicated. So, but the spirit is the same. So in the same example that I described before, let's look at this example. There's nothing in the lower arm equal to 3. There's nothing to the left and nothing below it to the right. So it's just 8x3, 1 by x3. Let's look at something which has a t. So let's look at this cell. Okay. If you look at the lower arm that contains these cells and the cells below it, to the right, there's nothing. But there is one cell here which has content 3. So I get t by x3. Okay. And here, if you look at this one, which one am I looking at? Yeah, this one. Okay, this may be a typo. No. Yeah, sorry, this is a typo. There's nothing equal to 1 in the lower arm. No, so sorry, this should not be a t. And I'll describe the projection which leads to these states of the multi-species states. So our first theorem is that the stationary weight of this process, stationary weight of any tableau in this process, is t to the quinv of sigma times x to the sigma. So we don't have the match. Remember, q is 1. So we only have the quinv. And somehow all of this is encapsulated here. And therefore, because of our previous result, the partition function, which is just the sum of these things, is just the modified Macdonald polynomial at q equal to. Okay? Okay, so as I remind you again, oops, sorry. Where am I? For now, our theorem works in general, but for now I'm only talking about distinct parts. Okay, so now let me answer Amri's question, and how do I describe the lumping? So I'm going to now associate to every tableau, I'm going to associate a configuration of the multi-species TAZRP, remember? So what am I going to do? So rather than reading this, let me just show you what you do. You look at the bottom row, okay? And look at all the numbers in the bottom row. If, so in this example, there is a 3 at a bottom row of of a column of height 1. That means there will be a 1 in position 3. There's a 2 the bottom row of a column of height 2. Okay, there are too many 2s, but that means the 2 is going to be there. And this is a ditto for this 2, so there will be a 1. Okay, so depending only on the content of the bottom row, we get a projection. And part of the reason for the complication is in when there are repeated parts, like this example, we have to, so we get contributions from both things, like where everything else is fixed and the bottom row of these two are interchanged. These two, if you compare these two and these two. And these. So that's basically why there's a lot more complication. And so because of this lumping, we prove our results, which says that the stationary probability of a state tau of the multispecies TAZRP has this formula: t to the quinv, x to the sigma. So where you sum over all tableaux which project to tau, where the projection is through the bottom. Okay, and basically one shows that this map rho, which is the projection, is compatible with these two generators of the stochastic process. So let me just show you this running example. So if you look at all tableaux that contribute to 2 1s / 1, that means there has to be a 2 at the bottom row of a column of height 1 and 1s otherwise. And so there are 4 possibilities. And if you sum all of these, so the content of all of them is, So of these 2 is x1 cubed x2, and of these 2 is, that's a typo. It should be x1 squared x2 to x2 squared. And if you sum all of these, they factorize. And if I go back to this example, this is this one. Okay. Okay, that's this thing that I mentioned. Okay, so let me tell you some more remarkable properties of this process. So suppose tau super j sub I is the random variable which counts the number of particles of type j at site I. Then we'll denote expectations in the stationary distribution by these angular brackets. Then first we have this elementary symmetry property which I mentioned, that tau j1, if it's a function of x1 through xn, then tau ji will be a circularly shifted, the same functions with circularly shifted indices. And okay, so now let me go back when there's just one kind of particle. So in that case, the stationary probabilities have a very simple formula, and using that I can give you a formula for the density. So because of this proposition, it's enough to look at densities at the first site, because I can just rotate and get any. So, and using this, we can show that the density of the jth species of particle at the first site is given by x1 times d by dx1 of the log of the ratio of 2h tildes. Okay, so it's a very clean formula. It's very easy to prove it. And one thing I wanted you to notice is that these are symmetric functions, of course, in x1 through xn. But I'm breaking the symmetry with respect to x1 because I'm explicitly differentiating this by that. But therefore, it is certainly symmetric in the other n minus 1. And I'll come back to that in a second. So the other result we have is about local correlations. So suppose you are, as usual, considering the TAZRP of type lambda on n sites, and now you fix a small l number of sites. Okay, you fix some small l, and you fix some content in that. Okay, so W is the configuration where certain subspecies of particles sits. Okay, so let's say if lambda has 5 ones and 4 twos, maybe we want W to be 2 ones and 1 two in the first two sets. Whatever, you can prescribe whatever you like. And we will consider two types of local correlations. The first is when we look at the stationary probability of having exactly content W1 to WL on sites 1 through L respectively. Okay, and the other one is having at least that content. You could have more, but you at least want that much content. So, and so for example, if lambda is 2, 2, 1, 1 and n is 4, you could say L is 2 and W is 1 stroke 1. So that means configurations that are contributing to this W bar probability are things where you have 1 stroke 1 in the first two sites and nothing else. So the other two twos should sit in the last two sites. So these are the three possibilities. And these of course also contribute to the W hat, but in addition you could have twos in the first two sites as well. So you could have both twos on the first side, both twos on the second side, 1, 2 in the first side, etc. in all possible ways. So you have extra control. And our theorem is that both of these quantities are symmetric functions of the other variables, xl plus 1 through xn. Okay? So they are not symmetric in x1 through xl. I mean, of course, the denominator is always symmetric. It's a modified Macdonald polynomial. But the numerator will always be symmetric in xl plus 1 to xn. And to our knowledge, I mean, such kind of symmetry result has not been observed. And two special cases are that when you set L equals 0, which means you don't impose anything, you get the full partition function symmetry. And when you set L equals 1 and W equal to just J, and you look at the hat correlation, then you get that it's symmetric in x2 to xn, as I showed you explicitly. And the idea of the proof is non-trivial. It uses an expansion in terms of this important family of symmetric polynomials known as LLT polynomials, Lascaux, Leclerc, Thibon. And yeah, so for this previous example, if I look at this W hat thing with n equal to 4, you have to sum over tableau with these bottom rows and anything in the top row, and it will turn out to be a symmetric function. It's a bit complicated to write down. I mean, the expansion is quite large, so I didn't write it down explicitly. So let me end with open questions. So as I said, the in when Quinn definitions are very similar, but there doesn't seem to be an bijective proof giving equality of those two formulas for the modified Macdonald polynomial. And as you asked, as Mohan asked, I mean, we would naturally want to generalize this to arbitrary Q, but this seems difficult. So these H tilde at Q equal to 1 has many nice properties. It has this factorization which we lose, and we expect to lose translation symmetry. I don't think there's any way you can put in the Q and still have translation symmetry. And that sort of makes it harder to guess and play around with it. So, I mean, this I think is doable, but it's not going to be particularly easy. Okay, with that, I'll thank you for your attention.
So, any questions?
Should you use the factorization?
Use the mic.
Do you use that factorization of H tilde lambda at Q equal to 1 for your proof?
No, but actually, yeah, so since you asked this, I can blabber some more. So the multispecies TAZRP is a process on the ring, right? With you have 1s, 1, 2, 1, or something, 3, 1, like that. What, what turns out, and I had flashed that slide by very quickly. Let me go. Sensitive. Yeah, so there is one can write down a multi-line process. So so if you have k species, which means k distinct kinds of particles, you can write a process of height k minus 1 and of course n as before, where each row is a single species particle. Is a configuration of the single species TAZRP. So you can have one, but the contents will increase as you go from top to bottom. So you can have things like that. And, let me put it here, and so I have 3 here. I'll put 2 here, and I'll put 1 here, like that. Something like that. And this will project onto this. And what happens because of the factorization is this h tilde lambda, each of these is one of the factors. And what more things turn out to be true, as you run the process, suppose you just stare at the third column. Then that process, the marginal process, is also is a single species TAZRP that I first mentioned. So any row is independently, if you just stare at it, it looks like a single species TAZRP. And with that particular factor h tilde as the partition function. So all that niceness is there. And somehow when you put q equal to 1, all of that is going to break. It's going to not be so nice probabilistically anymore. But of course, it will be nice to have something which captures the full modifier.
So I have another question. So I'm just a little lost on the flow of the arguments, in the sense of, so on the one hand you mentioned your result which gives h tilde lambda qt in terms of this L things, right?
Yes.
So that is an independent.
Yeah, that's purely combinatorial and independent.
Okay, so that is independent of all of this.
Yeah.
So this M TAZRP.
I mean, the reason we started working on this is because of this connection also. I mean,
right.
I mean, you already so you could ask, the Hagelin-Heimann already have a formula. Why are you working on another formula?
Right. No, I mean,
so
I understand.
So that was the reason.
Motivation comes from there.
Yeah.
But in terms of logically, what follows from what? So you're saying that's an independent thing altogether.
Yes.
Then there's this tableau process for which the stationary weight is given by q in and so on.
Yes.
That is for that was only at q equal to 1. Right?
Yes. So for this process for this processes, we only have at q equal to 1. We do not have anything more than that. And we use the first thing to show that the partition function is h tilde lambda, right? Because the weight of any tableau is t to the quin x to the sigma. And we know from our first result that the sum of all these things is going to be h tilde at q. So we use that.
I see. So that implies that this is actually h tilde specialized at q equal to 1.
Exactly.
And then this projection enables you to compute the M TAZRP.
Yes.
Is that right?
Yes.
I see.
So for any fixed bottom row, we look at all the things that project to it, which just not fixed bottom row. Any fixed configuration of the TAZRP, you look at all tableau with bottom row which of that particular kind, and top rows anything, and that will sum to that.
So is the tableau process, I mean, why study the M TAZRP at all? In the sense, sorry, just playing devil's advocate.
Yeah.
So why is isn't the tableau process, already an interesting thing in its own right?
Yeah, absolutely, yeah. So I have only mentioned observables involving the TAZRP, but there are also nice observables on the tableau itself, and we have some results about that. So for example, one nice consequence is that suppose I have, so I'm again using the diagram notation. So suppose I have some something like this, I don't know. Suppose I only describe the content here in these cells in a sub diagram. Then this is independent of anything below it. It just turns out to be the case. Oops. So there are observables like that. So I mean, there are nice properties of the full process on tableau also, which is also.
Okay, so last question. So this, I mean, given that you're only doing this at q equal to 1, where h tilde, you wrote out an actual explicit expression for h tilde lambda, right, as a sum over partitions.
Yeah.
Yeah, and binomial coefficients and so on.
This one.
So this monomial, the monomial expansion.
Yeah.
So, I mean, somehow it seems like this is a much simpler instead of the q. I mean, the qn is sort of a new thing that you have sort of noticed, right? I mean, is there any way of just directly using this formula to realize that the stationary distribution is the, I mean, the stationary distribution is given by this formula essentially, right? The partition function.
Products of these.
The products of these, yes.
Right? It's not just this.
Okay. But didn't you say, oh, I see.
Because h tilde of lambda will be a product of h tilde of things with only ones.
Okay.
And this is going to be the, so I had mentioned it later, I flashed by it. So if you have a single species thing, then this will be the denominator. So let me go back there. So you see, the stationary probability of any configuration tau will be that sum that you just saw times this multinomial coefficient.
So the single species thing doesn't determine the multi-species in any easy way?
No, because you see they're coupled. The rate at which something hops depends on how many things there were above it. Yeah. So
okay.
Yeah. So there's a complicated relationship, but somehow things still factor, which is kind of why it's interesting.
Okay. Oh, yeah. Thanks.
Yeah.
Any other questions? Yeah.
So this h lambda tilde at q equal to 1, is it some plethysm of E with E plethysm something?
I don't know if there's a specific way of h tilde lambda is, do you know what j lambda is? The integral form of the Macdonald polynomials?
I know p lambda at q equal to 1 is E lambda prime.
No, this is
that
not.
way it cannot
No.
Okay.
So the construction of h tilde is itself complicated. You have to do some plethysm on j lambda, the integral form.
No, but that's just some multiple of, you just multiply by.
Yes, to obtain j lambda from p lambda. Yeah, but then the action of plethysm is a bit complicated.
Yes. Actually, I think you get h first, and then you need to do a further transformation.
Yes, exactly. Yes, right.
Yeah.
That's why the tilde is.
Okay.
But I don't know if there's any direct way. But the h tilde is so simple, one can just write it down without saying much more. I mean, one can just define, where did it go? One can just define the h tilde as this way, right? You could say this is one natural way of natural quantity, and then you take product. One could just say that, but it's poorly motivated. But so one could just define it this way and not very. But as Vishwanath says, I mean, you lose the Q, you lose lots of things which make it more interesting.
And how did you come up with this, L thing, this gamma versus L thing? I mean,
so this was the conjecture of the CHMMW. So when they were proving their compact formulas for Macdonald polynomials, they somehow noticed the connection between these gamma triples and L triples. And first they thought it was kind of strange, maybe coincidence for small cases, and then they systematically did many large cases, and then it was still turned out good. So then they left it as a conjecture. So I should say our proof for that follows Hagelin-Heyman-Lur's general strategy. There are a lot more technicalities one has to take care of, but the general proof strategy, again using LLT polynomials, there's a lot of machinery that's involved. It's which I should say Olya, my collaborator, is the master of. So followed her general approach.
So that's this thing that Q inv and inv that they. So you don't expect a nice bijective proof. I mean that's absolutely amazing.
We thought there has to be one. I mean, so I think we came up with one when you have only 2s and 1s. So like this, when you have height 2. But even that was quite messy, and we didn't quite see the point of.
You had a proof, right?
For that case, when you have only 2s and 1s. Okay, I don't know. It seems like such small progress. It's not even worth mentioning.
But then sometimes it's nice, right? To argue that there is no nice bijective thing, come up with a second statistic, and then that behaves very differently for inv and q inv. So you enumerate, in with an additional statistic, and then it's. Have you tried that?
No, we have not. We have not tried anything more complicated. Yeah. I don't even know what happens if you take the joint distribution of inv and quin. Maybe that is something to consider. Yeah.
I have a sort of naive question. This idea of using a process, defining a process on a tableau and then lumping it, is this something that's been done before?
So this thing that I mentioned on the cylinder, that has been done before, and this tableau is just one higher generalization. So we have a process on this that lumps to that, and we have this tableau that lumps to that.
Okay. Yeah.
So it's just one. People have done similar things, but maybe not exactly the same.
It's the first time I'm seeing. But that doesn't mean anything.
Yeah, but this idea of proving a nice combinatorial formula for the stationary distribution of a process in terms of a process that's enriched, which lumps to it, is an old idea. But of course, depending on the problem, they'll be different, and the actual combinatorics of the thing, you will have different enrichments, of course. Yeah. But yeah.
Okay. So I don't know. There are no questions. There's one question on the YouTube chat, but I don't really understand the question. Rajat Singh wants to know why a continuous random process is ambiguous.
Ambiguous?
I don't understand. It's hard to calculate.
Yeah, so right. So what can happen if you have a continuous time process on an infinite graph with infinitely many particles? Then you could have some things called explosions, where infinitely many particles move in as soon as the process starts, and then the process doesn't make any sense anymore. So such things can happen. There are things called Feller processes, and there are all kinds of conditions that are needed to make sure that the process is
continuous time is an essential requirement for these kinds of proofs, or you could also.
No, one could do it. Continuous time is natural because in a continuous time process, only one particle moves at a time.
Okay.
You could say
make something that is discrete time, which ends up with the same
stationary distribution. But so you will have to engineer it. You will have to say, okay, one time only one particle moves. Otherwise, it's natural to think that every site has a clock, and whenever the clock rings, this particle moves, and with probability 1, 2 particles will not move at the same time. So that's the usual reason.
Okay. Any more questions? No? Okay, in that case, there are no more questions on YouTube either. So let's thank Arvind.